Let's start with the first example to calculate eigenvectors and eigenvalues of the following matrix. A equals 3, 0, 0, 1/2. So the first step is to calculate the eigenvalues. And as you know, the way we do this is that we calculate the determinant of A minus lambda I, and the result must be equal to 0. So what's the determinant of this matrix? So this will be the determinant of matrix A minus lambda times the identity matrix, which has 1s in the main diagonal. And the result of this determinant is equal to 0. So we do the subtraction of these two matrices. So 3 minus lambda, 0 minus 0, 0 minus 0, 1/2 minus lambda. The determinant of that matrix must be equal to 0. So the determinant is simply this times this minus this times this. So we basically get 3 minus lambda times 1/2 minus lambda equal to 0. So we have arrived at the characteristic polynomial. So this, we call it P of lambda. It's a polynomial called the characteristic polynomial. Now, in this example, it was very simple because we already have the polynomial factorized. Normally, you don't get it factorized directly. So whenever these two terms are not 0, we would have minus something else. So that would not be factorized. So then you need to expand the polynomial and factorize it into the roots, okay? But in this case, it's already factorized, so we know that the roots will be equal to the eigenvalues. And what are the two roots? They are the solutions to the equation polynomial equal to 0. So if lambda equals 3, this will be 0, so that will be the first solution. And the second solution will be if lambda equals 1/2, this will be 0, and that will be the second solution. So those are the two eigenvalues for this matrix. Next, we have to calculate the eigenvectors. Now, normally this is a relatively fast procedure, but since this is the first example you are ever have seen about calculation of eigenvectors, I'm going to show you different ways of doing it, okay? Normally you would just choose one and just do it, but I'm going to show you that there are different paths and they are all equivalent, that you always end up with the same result. So what we have to calculate is, so now we know that A lambda, so A times vector V equals lambda times vector V. That is the definition of the eigenvalues and eigenvectors, right? So we now know what values lambda can have. So lambda can either be 3 or it can be 1/2, okay? And for each of those two values, there will be associated eigenvectors, which are this eigenvector here. Therefore, you first start with one eigenvalue. So you say case 1, when lambda equals lambda 1, which is equal to 3. So that's the first case. So then we need to solve the system A times V equals 3 times V. Okay? So what is A? So A is 3, 0, 0, 1/2. V is an unknown, so let's write it as Vx, Vy is equal to 3 times Vx, Vy. So we need to solve this system of equations. So if you write it explicitly, this is two equations. 3Vx plus 0Vy equals 3Vx, and 0Vx plus 1/2 Vy equals 3Vy. So two equations and two unknowns. So if we subtract the right hand side on the left for both equations, we arrive at 0Vx plus 0Vy equals 0 as the first equation, and 1/2 minus 3, that's minus 5/2 Vy equals 0. So we arrive at these two equations. Now, before we continue, the solution to these equations is obvious, but before we continue, notice that sometimes you can save steps by directly going to a minus lambda I v equals 0. Okay, so remember this equation and this equation, so let's substitute lambda equals 3, a minus 3i. So these two equations, they are equivalent. So as I showed you in the theory video, it's just that you put this subtracting in the other side, so you get minus 3i here. Yeah. So they are the same system, so the solutions are the same. But by doing it in this way, now we can say a minus 3i. So it will be 3 minus 3, 0, 0 minus 0, 0, and 1/2 minus 3 minus 5/2 times v, which is vx, vy, equals 0, 0, which gives you the equations 0 equals 0 and minus 5/2 vy equals 0. So you can see that you arrived exactly at the same point, but a bit faster. And we simply did it by doing a minus lambda I, which you have it here anyway, this matrix here, that's a minus lambda I. So we just substitute lambda with the number, okay? So those two completely equivalent paths. Now, how do you solve this system of equations? So in this case, it's really simple because they are almost already solved. In general, this might be a system of equations which might be bigger than two equations. For example, if the matrix was a 4×4 matrix, this would be a system of 4 equations with 4 unknowns. So in general, one way to do it is to do Gaussian elimination. But in simple cases like this one, we don't need to do it. So what is the solution to this system? So it's obvious. Vy must be equal to 0 from the second equation. And what about Vx? Well, any value of Vx is allowed, and these two equations will be true anyway. So Vx is a free parameter. So Vx is equal to alpha. Okay? So that's our solution. The solution is that V equals these two unknowns, which now we solved, and they are equal to alpha 0, which you can write as alpha times the vector 1, 0. Okay? Now, as I promised you when we were studying the theory, the solution to the system is always written like this: alpha times a vector plus beta times a vector plus ... yeah. So in this case, we only have one vector because the nullity of the matrix was 1, so there is only one dimension in the solution. So we know that this will be our eigenvector. Yeah. If we have found 2 degrees of freedom, then we would have seen we have 2 vectors, and those 2 would be eigenvectors. But in this specific case, we have the solution in this form, so this is our eigenvector. So indeed, we have the solution as alpha times a vector, so this is our eigenvector. So in summary, we can say that for the eigenvalue equal to 3, the associated eigenvector is equal to 1, 0. Now, the fact that when solving this system of equations, or this one which is equivalent, we arrived here, in which one of the two equations is 0 equals 0, and it brings no information, this is not a coincidence, okay? The reason why we have gotten 0 equals 0 is that the matrix A minus 3i, we know that the determinant is equal to 0. How do we know it? Because we designed it in that way. By asking this determinant to be 0, we found that one of the solutions was lambda equals 3. And therefore, when lambda equals 3, the determinant of this matrix must be 0. And that is why V has infinite solutions. And that is why one of the two equations cancels out, because we have 2 unknowns, but we need infinite solutions. So we can only have one equation. Okay? So that will always happen when you solve for eigenvectors. When you will always find that one of the solutions goes away, one of the equations goes away, so that we have at least 1 degree of freedom, which is this parameter alpha, and that's why we can find the eigenvector here. Okay, so that will always happen. Next we have to do the case 2, which is the second eigenvalue, which was 1/2. So now we need to solve, again, the same system. Either A times V equals 1/2 V, or the equivalent system, A minus 1/2 identity matrix times V equals 0. Yeah, they are equivalent, so we can choose to solve one of them. So let's go perhaps with the one on the right. So a minus a half I, we have to do 3 minus a half, that's 5 halves, then 0, and then a half minus a half, that's 0, times vx vy equals 0, 0. Okay, which means that 5 halves of vx equals 0 and 0 equals 0. So what is the solution? That vx equals 0 and vy is a free parameter because it can take any value, so we call it alpha. So for the case lambda 2 equals 1/2, we have that v is equal to vx is 0 and vy is alpha is the free parameter. So okay, let me actually write v equals alpha times 0, 1. So now we know that this is our eigenvector. So that's what I can write here in the final answer. Let's check in my applet if this makes sense. So here I'm using the matrix 3, 0, 0, 1/2, and you can see that for any input vector v, we get these output vectors a of v. So now let's test our solutions. We have the solution that the vector 1, 0 had an eigenvalue of 3. So if we put the vector equal to 1, 0, bam! Indeed, when the input vector is 1, 0, the output is 3 times 1, 0. Yeah, so indeed the eigenvalue is 3 and the eigenvector is 1, 0. And the other result we found was an eigenvector 0, 1 with an eigenvalue of 1/2. So indeed, if we put v equal to 0, 1, you can see that perfectly a of v is parallel to v and it's 1/2 of the length. So indeed the eigenvalue is 1/2 for the vector 0, 1. Notice that any vector on this line is an eigenvector because a times v is always 1/2 times v. And also any vector on this line is an eigenvector. Okay, so not only 1, 0, but 2, 0 is also an eigenvector and 3, 0 is also an eigenvector. Actually, the span of 1, 0 is what is called the eigenspace. So actually, we could say that the eigenspace is the span of 1, 0. So the span of the eigenvectors is what we call the eigenspace. And here we would also say that the eigenspace is the span of vector 0, 1. Normally, people just give 1, 0 as the eigenvector. So this is the usual answer that every book lists. But the truth is that you could have been given 2, 0, for example, and it would still have been a valid eigenvector, or 3, 0, or 1,000,000, 0, or minus 3, 0. You can always scale an eigenvector, and the result is always also an eigenvector. So there are infinite possible solutions. So one way to be as general as possible is to say that the eigenspace is the span of this vector. And then you are including all of the possible infinite eigenvectors. So I personally, if I could rewrite all of the maths books, I would encourage everyone to use this notation. But all of the books and all of the online material you will find just give the eigenvector like this, and they are done with it. Yeah, knowing that there are infinite possible answers. Okay, thank you very much for watching. Let's look at another example.